Fast search is not only about better hardware. Impact-ordered indexes let the rankers skip weak postings before they waste scoring time. You'll learn the shape of a workflow that builds an impact-ordered index and ranks top documents while skipping low-impact postings. I'm Professor Pi, teaching search and IR with simple Python. Search systems need to find a few best documents quickly from many candidates. The hard part is scoring. Modern rankers use many features, and that scoring can be expensive. So, the common trick is to prune early. Impact-ordered indexes are a pruning strategy that reorders posting lists by the potential contribution of each posting. That lets a query evaluate the most promising matches first and skip the rest safely. At a high level, impact ordering answers a simple question. If I see a posting that can only add a tiny amount to a document score, can I ignore it without changing the top results? The intuition is like reading only headlines that sway an election. If a remaining candidate cannot catch the leaders, even with all remaining good hits, you skip it and save time. We will build a tiny toy pipeline so you can see every move. You will load 3 short documents, turn them into posting lists that show impacts, compute upper bounds, and then run a safe pruning loop that returns the same top 2 documents while touching fewer term matches. This makes the core idea concrete and executable, not just an abstract claim. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To begin, we will show the naive baseline so you can feel the wasted work before we optimize. This snippet surfaces the baseline doc ID ordered scan effort for our toy corpus. How many documents would you touch if no pruning lived between the query terms and the heap? We load 3 short documents into the docs.Dict, feed them through default-backed postings list, and grab every document ID containing any term from query terms. That comprehension builds naive docs, the full candidate set the engine must score before any smarter strategy kicks in. The printout, docket scan candidates equals 3, confirms every document would be scored, underscoring the wasted work we will trim next. Now that we see the waste, we need a way to score postings by how much they could move a document rank. So we compute per posting impacts and order them. This example converts those postings into impact-sorted lists ready for upper bound pruning. Our question is how to assign realistic term weights so that high-impact matches rise to the front of the queue. We apply counter on each document string, multiply term frequencies by the IDF lookup, and push impact doc pairs into impact lists. Sorting the lists in descending order means the heaviest contributions appear first, which later stages can exploit with tight score ceilings. Seeing impact top score equals 1.45 tells us the impact term can at most contribute that much per document, giving a concrete pruning reference. With impact-ordered lists, we can still compute a baseline ranking by adding every impact, term by term. That gives us ground truth to compare pruning against. This code runs a term-at-a-time accumulation pass to establish the unpruned top K baseline. Want to know the ranking you'd get if you dutifully added every impact contribution before pruning anything? We loop through impact lists per query term, update scores with additive impacts, count every term doc pair in scanned pairs, and finally let heapq.largest pull the best 2 documents. The intermediate list view wraps the floating scores to 2 decimals so we can compare it later against pruned runs. The output baseline top K is 1 3.2, 2 1.55, scanned pairs 4 is our ground truth ranking and work tally. Next, we need a way to predict how much extra score a document could still collect from unexamined postings. That prediction makes pruning safe. This snippet computes per-term tail bounds for pruning decisions. The open question is how to predict the remaining score budget a posting could gather from yet unseen terms. Term max pulls each term's top impact from impact lists. We sort ordered terms by those ceilings. And the reverse sweep fills tail bounds with the cumulative slack of later terms. With that map, a retrieval loop can check whether a document plus its residual headroom can beat the current heap before doing more work. The printed dictionary confirms pruning retains 3.0 impact in reserve, while impact already spent its budget. Finally, we apply those tail bounds in a retrieval loop and skip postings that cannot improve the top K. This example applies those bounds inside a pruning loop to skip hopeless postings. We want to verify that the tail ceilings let us avoid work, yet still return the correct top K. Scores and heap keep the accumulated impacts and current threshold. Best total blends the new impact with tail bounds, and any posting below that floor bump skipped without touching the heap. Surviving postings add their impact and refresh the heap-driven floor, so later checks stay tight. The final print shows the unchanged top K plus 1 skipped pair, demonstrating safe pruning trimmed the stand. This toy flow maps directly to larger systems. The impact values become feature contributions in a real ranker. Tail bounds are computed per query using the same idea. In production, you would store impact-ordered postings on disk and stream them for each query, instead of building them on the fly. Impact ordering is simply a way to put the most influential hits first so you can stop early. Use it when scoring is costly and you only need the top K quickly. One important caveat: your impact estimates must be conservative and well calibrated. Otherwise, you can accidentally drop a correct top result. Next step: scale this pipeline to a bigger corpus and add timing checks. Measure saved scanned pairs and confirm the pruned top K matches the unpruned baseline as you raise document count. If short, practical IR helps, subscribe and watch the IR videos.